You know that the first exercise is to implement BCJR and a convolution code. I want this to be submitted. But started. Friday 21st. Okay. Okay. I have to implement map. Map. It's a variation of the okay, so let's get started. Remember we had this first state is and we start at t equal to 0, a known state. Okay. Labeling, we consider rate half encoder. The labeling is such that these are the outputs of the encoder. 0 for all 0 sequence. Input bit is 1, you end up with 1 1 as the output. Well, you can draw the trellis, given the inputs, you can figure out the outputs and everything. This diagram so that once we complete this algorithm, come back and well, ST is the state of the encoder. Okay, IT is the block of. Well, IT is the input, zeros and ones to the encoder. ST is the state, and ST is defined as IT minus 1 all the way to I minus. We assume that the encoder starts in an all 0 state, okay, and it ends up in an all 0 state. So in the end, we have to assign a few known states so that it will end up in the all 0. Okay. So if you give capital T bits length of is T, but have T plus V output to have tau equal to T plus V, T being the number of inputs or the length of the input. Okay, the length of input T followed by T zeros. You have T input bits followed by V zeros, and the encoder is in an all zero state. Total length is T plus V, and the last state will be all zeros because these zeros will flush out the shift propagate through and end up in the state is basically the contents of the registers. Right? So the overhead involved here is let's go through the BCJR algorithm with this. So what is our objective? Our objective is to find the APPs for the source bits, probability of ID equal to 0 or 1 given the entire received sequence. Or we may want to find the APPs of the channel bits. What are the channel bits? We denote them as channel bits are denoted as x of t to t prime is given by xt plus 1 all the way to xt plus xt prime. Okay, and this xt may in turn comprise of 2 bits. It's again a vector. Okay, this xt can be a vector because for one input bit there are two. But this is the sequence of channel corresponding to xt1. We also have st to t1, st plus 1 all the way to st prime. These are the states associated with at each time t to t prime. Similarly, we have the channel outputs by t to t prime by t plus 1 by t prime. Again, yt may be a vector composed of outputs corresponding to each time encoder produce 2 output digits and corresponding to 2 output digits output of encoder it goes through a channel, and then at the output of the channel we may have yt comprising of elements. Okay. Here it is assumed that it is a discrete memoryless channel. You can extend it to machine channel. It is follows. In case of discrete memoryless channel, what happens is that this output is also discrete and it takes so many levels. Okay, yt it takes a fixed set of yt belongs to an alphabet of that's the only difference. But in the case of AWGN, it doesn't have the fixed size, it can take any value. Okay. we define the state transitions pt m given m prime as probability of st equal to m when st minus 1 is equal to m prime. So what are m and m prime and m? If this is m prime, it could be m. Probability of st equal to m given st prime equal to m prime. If you are in this particular state, what is the probability of reaching? Very simply written as probability of pt of m slash m. Okay. If you are in a given state, what is the probability of reaching this point? Okay. If this connection doesn't exist, it is 0. You can see that not all connections exist in this. That means if there is a connection, it is 1. If there is no connection, actually it is a mystic function. Right? And it's also independent of t because if the trellis is not time invariant, then it becomes independent. Not a function. Similarly, probability of then qt of x given m prime comma m equal to probability of xt is equal to x and st 1 is equal to m prime and st equal to m. You can see that t minus 1 is associated with m prime and t is associated with okay. Well, actually, in this case, we are in this current state, you can reach 2 possible x states, and since the inputs are equally likely, the probability of reaching this state from here is half. The probability of reaching this state from here is half, it's not 1. And then if there are no connections, obviously, the probability is 0, and we are not really interested in it because that's not something of interest. Okay, so the probability of reaching next state p of m comma m prime really depends on the input states. In this case, input is binary. It takes 2 values probability x either 0 or 1 probabilities okay, and for the remaining other connections they would exist. Not interested. In fact, you cannot reach from here to here. Okay, how about this qt of x? Okay, probability of xt equal to x. Well, of course, x can have 2 elements, right? So, given st minus 1 is m prime and st equal to m. So what about these properties? 2 connections are already specified, right? given these two connections are specified, so this state contains the past, heat, past T plus 1, past V samples, inputs, right? V plus 1, right? Yes, V plus 1. So, if you specify exactly this state and this state, then the output is deterministic, right? Specify these two states, the output is deterministic. Okay? So this is basically either 1 or 0. If there is a connection that exists, it is 1. If you take these two, there is no connection, then that property is 0. Here, if there is a connection, the probability is 1 over 2, because there, for all, if the connection exists, it's probably 1 over 2. In this case, it's binary system. And if the connection doesn't exist, obviously. Similarly here, either this connection exists or it doesn't exist. So this basically takes a distribution. Okay? Either 0 or 1, depending on whether the connection exists. Essentially, when you implement the decoder, you will have a lookup table, right? Given the current state, what is the next state? You will have a lookup table. That is fixed, and that is fixed throughout the time evolution. Given the current state, what is the next state? That doesn't change with time. That relationship is dependent on time. Given the current state, the next state is uniquely determined. That's a function of. Of course, you can have time varying values. We'll take one such example later. Okay, so now we'll go ahead and specify the BCJR MAP algorithm, and through part of the derivation, the other part was not complete. Okay. So we are interested in the outputs. Of course, at t equal to 0, we are in all 0 state. We are truly interested in starting t equal to 1 to till the end. Okay. What is the end here? Some tau here. Okay. Obviously, of course, last digits are known, but nevertheless, we are interested in t equal to 1 to tau. Okay, that's where we terminate. So the y is received from. We are interested in y1 to collect y between 1 to tau. What are they? y1, y2 all the way to y tau. We collect them. Okay. And the probability of y1 to any arbitrary t given x1 to t is probability of y given x. Okay. And this relationship is known to us, and this is basically a product over probability of y j given xj, j equal to 1 to 10. Is that right? The memory resist. Channel digits, y equal to x plus n, current received sample. This was the, sorry? One stops. Alright, so I have to open this a little more. Okay. this part, for, we are developing this for the discrete memory channel for it is AWGN. You know the property of yj given xj, right? Yj equal to xj plus nj, and if the density function for nj is provided, you can calculate. Okay, fine. Okay. We are interested in the APPs of the states as well as transitions. We'll explain why we need both. If you know the APP of a state, if you know the APPs of all the states, you should be able to calculate the APPs of the source bits. Okay, we'll show that in the end. And if you know the APPs of the transitions, okay, what are the states here? Well, at any given time, we have 1, 2, 3, 4 states. Okay. There are 4 states here. Okay. So if you know the APPs of all these 4 states, from that we'll be able to find out the APPs of the input bits writing. Okay. And if you know the APPs of all the transitions between any t minus 1, any segment t minus 1 to t, you know the APPs of the all the transitions. There are many transitions, right? From these transitions, you can calculate the APPs of the channel bits. What are the channel bits? XTs. These zeros or ones. See, your exercise that I'm going to give you are only interested in the APPs of the source bits. You are interested in demodeulating the source bit. You will get the soft output. From that you can get the hard output. But in some systems like in turbo codes, you are also interested in the APPs of the channel bits, and then you will feed it back to another code, the exchange. So this algorithm provides APPs of both as well as channel. Source bits are input to the encoder, channel bits are output to the output of the encoder. So we are interested in probability of ST equal to M, because probability of a given state taking a value, M takes 4 values, right? This case, generally you can take a given the entire receive sequence 5 to 5 1 to top. So we observe the entire receive sequence. Actually, you have to receive all the samples. Okay, and calculate these APPs. But in real life, you may start implementing the algorithm as soon as the first sample. Start the processing, you can go all the way to the end, but then you will see that you need a backward recursion. So you need the last samples before you start. That's an increase. This is equal to, you'll use the Bayes rule repeatedly throughout. So I'm not going to go through it. That is equal to probability of M 5 1 to tau divided by probability of 5 1 to tau. And we will see that this scaling is not of much interest to us, especially when you look at log likelihood ratios. When you do the actual map algorithm, even the scaling you have to calculate explicitly. At every stage, you can only calculate the numerator part and sum up all these probabilities to 1 and then figure out the. You assume a constant and sum up all these probabilities to 1 over all the possible states, and then you can find what it is. Normalize it. Okay? So we are really interested in this. And we are also interested in probability of st minus 1 equal to m prime. This is the joint probability we are interested in. And st equal to m. Basically, we are saying that this transition connecting one state to the other, but there are many such feasible. Probability of st minus 1 equal to m prime to and st equal to m given the entire received sequence. And again, this can be written as probability of st 1 is equal to m prime m given it's divided by probability of by 1 to 1. So again, we are interested in. Now we will find an algorithm to calculate this and this. Well, there are some intermediate steps. Okay. So for ease of exposition, we will first consider two functions. Lambda t of m that is equal to property of st equal to m and y1 to not 1 to how m prime m. And basically we are saying that we will consider the numerator part in each. Okay? And also we made the notation a bit simpler by just calling lambda t of m. Okay? Okay. These are the well, basically we're interested in these joint properties. And if you know these two joint properties, then we'll be able to figure out the APPs of the source bits and the channel bits that we will show later. This algorithm, although it may seem cumbersome during the mathematical development, once it is developed, especially when you invoke this interpreted down. Let me erase this, bring it back again later on. Algorithm is completely done. We'll introduce these probability functions alpha t of m. The joint property st and y1 to through t. So the difference between this and this is that this is the entire received sequence, but here we are going to consider the received samples, received 1 through t. T is the current time. That is a major difference. Beta t of m, the probability of by t plus 1 till tau, probability of by t plus 1 to tau. Here we consider only 1 to t, here we consider from t plus 1 to tau. Given st equal to m. Given that you are in the current state, what is the probability of by t plus 1 to? That's of course a long vector. And gamma t of m prime comma m equal to the probability of st equal to m and y 1 equal to m. What this says is that we are in the current state at some time t, and we know the current received samples associated with the coded bits, in this case yt. Yt has two elements in this particular example, right? And what is this joint probability? Okay, so basically we are at t equal to t minus 1 and this is t equal to t. Then there is a connection given we are at this state at t equal to t minus 1. What is the joint probability of reaching st equal to m for this one of these two given this thing? We want this joint probability. That's what you see that all the recursions will be written in terms of these probability functions. First, using these probability functions, we will show that lambda t of m can be written as probability of st equal to m and by 1 to t, not the entire tau, by 1 to t multiplied by probability of st plus 1 it plus 1 to tau given st equal to m comma y 1 to. Now these relationships, how we get from here to here, I leave it as an exercise. All repeated application of base. Sometimes you will apply it twice, sometimes you apply it thrice. Okay, I think we applied maximum 3 times. Basically, you write this y1 to tau as y 1 to t, and then y comma y t plus 1 to tau, and then apply base 2, and you will. Okay, that is equal to, well, this part is what? Alpha t of m, and this part is equal to probability of y t plus 1 to tau given st equal to m, and it will be this part y1 to t disappears because the state st is known, events of time t do not depend on. Okay. So the events after time t do not depend on y1 to t because of the numerical. Then if you ignore this part, this is defined as beta t of m. So what it means is that at any given stage in the trellis, state probability function, well, actually once it gets normalized, it is the state probability, right? Conditional state. Basically it's APP, conditioned on by 1 to 2. Okay. That is basically a product of alpha t of m and beta t of m, and we will show that alpha t of m can be written recursively, coming from beginning to the all the way to this forward direction, and we will write that beta t comes from the known end state all the way back. Compute this alpha t of beta t, but essentially the APP of the state st equal to m given the entire received sequence, basically the product of two terms probability functions dealing in the denominator. Quantities can be written computed recursively, one going from the forward direction, other coming from the backward direction. That's why we have this forward backward. So how this define, we already introduced this gamma t of m prime comma m, we already introduced it. Okay. So what we will do with this is that we'll break this into three parts. Essentially, y1 through tau, we'll write it as this part, y1 to t minus 1 by t, then by t plus 1 to tau. We'll write it as three separate, basically they are all vectors, right? So with three. Once you write it as three, it's like a joint property with 1, 2, 4, 5. Random variables here. Then you will apply this Bayes rule repeatedly. Right? When you do this manipulation, you have to carefully observe this. That will be the first part, property of st minus 1 equal to m prime is joint property, and by 1 to t minus 1. So I have taken these two, and the rest of it is only these two. Then we'll apply Bayes rule such that then we'll end up with the next part, property of st equal to m, we'll keep this guy right here, comma yt, okay, given st minus 1 is equal to m prime, that is the second part. And then there is the third part, property of y t plus 1 till tau, given st equal to m. Just have to write this Bayes rule several times. And that is basically equal to alpha t of m and gamma t of m and beta t of alpha t of m, beta t of m, alpha t of m, gamma t of m and beta t of m. Alpha t minus 1 of m prime, is it? Alpha t minus 1 of m prime, gamma t of m, beta t of m. Basically, this is the past, this is the current, this is the future. No, it has been derived. Forward backward comes from the theory. So basic idea is like this. Have a system with memory. So unless you observe the entire sequence, you can't get the evidence. Okay? So if you have a system with memory, what you could possibly do is, first of all, there is a dual list. Okay? Terminate. The Vaitarka algorithm was already known. So we know how to do maximal likelihood decoding. Maximal likelihood estimate of the transmitted bit stream. And it can be implemented using the Vaitarka algorithm, using the forward algorithm. You know that, right? But what we want is the APPs of the properties of source bits or channel source bits, let us say, given the entire receive. So the Vaitarka algorithm, we already have some pass merging here, pass diverging here. Okay. So what this algorithm essentially comes to, I don't know how they implemented it, but in any two stages t minus 1 to t, and if you are interested in the property conditional abilities of the source, take into account all the past received samples, then you take into account the current samples, and you have to observe all the subsequent samples that you would have received are actually received. Okay, and it turns out that when you start decomposing this, all you have to do is alpha t of m here, with alpha t minus 1 of m prime here, beta t of m here, that will capture those information that you have about this current input that has propagated through. Then you read the current samples. That will give you those. Actually, there are some approximations that you can always make. You don't have to start all the way to the end. Pages later, and then in fact, even in the Weiser algorithm, there are a lot of modifications made. Your time t, you can make decision about transferred t minus some t prime. A lot of approximations you make. But the point is, you have to allow, want to make a decision about it that is transferred time t. Can't make the decision at time t right away without observing some received samples. These samples contain information about it. Yes, it's so turned out that this algorithm observes the entire received sequence and delivers APPs, bit by bit or symbol by symbol. Although we call it symbol by symbol, but it still has some. How they have come up with it? Algorithm, very popular one, widespread application. Codes were developed. I was just told that this fellow Paul was from IIT, correct? They do cite that there were some other people who developed dated algorithms. First paper really comes up. Or BCJR. So there are a few Israelis and all is Indian, I don't know. Very elegant. Let's just proceed to the recursion. Also, I have to show you exactly how to get the recursion for t equal to 1 all the way to tau. Let's exclude t equal to 0. T equal to 0 is at known state. So it is alpha of 0 is 1. So state 0. And alpha 0 of m is 0 for m. So for t equal to 1 to tau, alpha t of m, you can write it as probability of st equal to m rather st okay. Write as probability of st minus 1 equal to m prime. St equal to m y1 to t summation over m prime, that is 0 to m. Is that okay? We have taken this probability and took the joint probability with even extra variable added st minus 1 equal to m prime, and we sum up over all feasible m prime. Is it okay? Huh? Now, you take the joint probability and sum out one of the variable, random variables with the margin. Okay. Well, that's a key step. That is equal to. Then, as usual, they will repeatedly apply Bayes' rule and do something. Okay, this y1 to t, you write it as y1 to t minus 1 and y. Once you do that, then this becomes probability of given 1, writing this given here that. Well, that turns out to be simply alpha t minus 1 m prime gamma t of prime gamma m. Okay, what that does mean? Something like this. We are here. What you do is get this forward metric at any given t. Let us say you have two paths coming from, it will not be from here, it will be from here also. Okay? You have two paths merging here, right? In the previous example, okay. It may not be two, but this is binary. There are always two paths diverging from any given state, and two paths merging can be. That's how that is. On the forward metric here, what this says is that take the forward metric, go 1, 2. Or whatever this, okay? Take the whatever the metric that anyway has been recursively computed. You take this metric, multiply with the transition metric. We call it metric because actually you can relate it to normalization. Yeah. Normalization. Okay. So you can think of this as a transition property, and this is a metric. It's a property. Take this metric, you multiply with the gamma t. You take this metric, you multiply with another gamma t. So this is different, right? Because the channel digits are. And you sum this product. And this m prime is over 2 because these connections don't. Although I have written it as m prime going from 0 to m, but actually there are two connections that are fixed. Turn out that similarly, to get this backward metric, take this metric, this metric beta, multiply with the transition property, add them up, then you will get the backward metric. And in fact, when you know this max log approximation, it turns out that relate to the difference. I'll talk about this so-called max log later. Take this metric. Okay, that's actually some sort of a distance. Add this distance, Euclidean distance between the give signal and digits, sum over. Right? There are two Euclidean distances. Take this total metric, take the accumulated metric, add the Euclidean distance corresponding to this channel digits. See which one is minimum. One is minimum, that is your new forward. That's exactly what we do in Recursive. So the max log, the forward only max log algorithm is indeed the Recursive. Forward only max log algorithm. That becomes the Recursive. That approximation is done. I mean, I'll come to that later on, or I will leave it as an exercise. AWGN case, you invoke the max log approximation. You can see the connection. First you have to understand this. So why there be algorithm? It gives you a maximal likelihood estimate of the source digits, source bits, or decisions. By definition, why there be algorithm doesn't give you soft outputs. This algorithm gives you the APPs of the source digits or bits or channels. So it gives you APPs. Okay, that is the fundamental difference. Convert the APPs into hard decisions. This is a symbol by symbol estimate, and ML is not symbol by symbol, it is a full sequence. In fact, it gives you one optimal sequence. It doesn't give you one optimal, but this gives you one optimal APP for each stage. But it gives you the optimal sequence. Turns out that in terms of the hard decision performance, it's simulated, although these are unrelated algorithms in some ways, that the performance difference is huge. The way of obtaining APPs. Of course, even the White algorithm has subsequently been modified to deliver software. I'm not going to describe so I can. Okay. In fact, there are many relationships. If you use the max log approximation, and you can see that White algorithm is already obtained, and if you go all the way to the end, and if you trace back, that's what is written. So the forward recursion, the max log approximation indeed delivers the algorithm. Trace back. So the end state is the beginning state. Trace back. Okay, that's the difference. But you may ask, what is the difference between SOA and MAP? There may be some small performance. SOA is probably a little less complex. There are also many variants also. Okay, so now just derive the expression for beta, then we will tell you how to get the APPs for the source beta. Again, somewhere here we made the fact that events after t minus 1 are not influenced by 1 through t minus 1 if current steady. For t equal to 1, 2 all the way to tau minus 1, of course, by tau minus 1, beta t of the tau of 0 equal to 1, beta tau of m equal to 1, and beta tau of m 0 for m not equal to 1. Okay. So you know that you're going to terminate it in last zeroth statements. I will erase this and write the recursion first. Beta t of m is equal to, when you introduce another summation, prime equal to 0 to m, probability of, let's see, beta s t plus 1 equal to m prime and y plus 1 to tau, we have y t plus 1 to tau given as t equal to m. But then we introduce this dummy random variable s t plus 1 equal to m prime. You are in the current state and you introduce at t, you introduce this. This is t plus 1. We are given y t plus 1, y t plus 2, and so on. You introduce this dummy state as t plus 1 m prime, summed up over forward recursion, but we introduce this dummy state. That becomes quite useful. Backward recursion. Equal to we only take the sample at s y equal to plus 1 and the rest is plus 2 to tau. Okay, and that comes here, probability of y t plus 2 to tau given s t plus 1 equal to m prime. And that turns out to be summation over m prime beta t plus 1 of m prime gamma t plus 1 m comma m prime. So what does this mean? Where at t minus 1, this is t, this is t plus 1. Okay. We want beta t of m here, okay? So we want beta t of m. And let us say we already know beta t plus 1 of m prime here, okay? Already know these two places, beta t plus 1 of, let us say, I don't know what it is, beta t plus 1 of 0 and beta t plus 1 of 0 and beta t plus 1 of 0, 1 of. So take this backward metric, multiply with the transitional metric. Take this metric, multiply with the transitional metric, add them up, and you got the backward metric. Once you know the forward and backward metrics, you know the APPs of the state. Well, not just APPs. You just know the APPs of this particular state. Okay. Fine. Okay. Now we have to add one more. Something about this gamma t, the transition. Gamma t of m prime gamma m is equal to was originally defined to be well, let's remove the summation. probability of st equal to m comma and yt given st minus 1 equal to m prime. Okay. Now this can be written as summation over the alphabet x, the channel digits x, probability of st equal to m given st minus 1 equal to, again this is a repeated application of this probability of, that everything is probability because all are discrete, not really dealing with density. So they are probabilities. Okay. But you can extend it to continuous. Probability of xt equal to x. Xt is the current channel digit. Of course, x is again a vector. It's not a scalar. Given t minus 1 time m. Then there is a third probability of yt given x. Now, after some manipulation, you can break it into 3 parts. Nice to do so because probability of yt given x, you can compute it, right? Probability of y given x. Okay, alright. That is the product, right? Product of probability of y1 given x1. But actually it's yt, so we just have to take yt has 2 components. So it's product of probability of st equal to m slash probability of st minus 1 equal to m prime. That is basically half and half, right? Depending on what the it's half and half that we discussed. And this one is something related to qt, is it? Is equal to, right here, summation over x qt of m given m prime qt of x given m prime comma m, and this is property of yt. You may be wondering why this summation is coming into this. Okay. What is x here? Yeah, basically, x is a vector with 2 elements. You have to carry this out for, these are all possible output symbols. So first term is half, second one is either 1 or 0. So what really matters is probability of yt given x. Well, I'll give an example that best illustrates the scenario, what this summation is. I think in the current scenario, this itself is a product of terms, right? Because yt contains 2 elements. So that is basically probability of yt0 given x0 multiplied with probability of yt1 given x. channel digits. We have channel is AWG sample. Entered from equilibrium raised to some minus something. One, this is well, one way of looking at it is what will have xt will have, let's say 0 0 here. Okay. The parallel transition visualization problems, you can encounter parallel transitions and reduce the zero. Let us say there are three pieces. Then there are parallel transitions. Okay. In that case, take the forward metric, multiply that, of course I'm talking about not just this part, you multiply with this, and basically branch metric will be summation over all these parallel transitions. Parallel transition will be ready to know, and the summation will come into. Right. Yeah. So in this case, there will only be a single term, right? What are the possibilities for x? So 0, 0, 1, 1, 0, 1, 1. So you can only have this next one, right? If you fix m and f prime and m, x is deterministic. If you fix m prime to m, the label is deterministic. You can take one of these possibilities. Okay. Then in this summation, only one will be valid, and for the rest of them, okay. I hope this having this half will be taken care later on. Let me give you this analogy. Fix these transitions. If at all x takes, let us say x has a cardinality s, and then it takes a subset of values, and for each x there is associated y by t. Then you have to sum over all those. Okay. Now we should be able to implement it. X-log map, what happens is that whenever you have sum of exponentials, in this you can already see that this algorithm, this is e raised to something and e raised to, basically it's an exponential. Like this here, that forward metric multiplied with this branch metric, forward metric multiplied with the branch metric, they'll all, this is an exponential, this is an exponential. Now we have sum of e raised to minus d1 plus e raised to minus d2. Let's say these are the metrics and this is what you want. And again backward metric will be something like that, and you multiply that with the transition. It can be approximated as, take natural logarithm of one will dominate minimum, right? E raised to minus min of d1 1 with the minimum distance, and that will become min of d1. So at every stage you can take this, the log of this logarithm of the summations. Then what happens is that point, if you want to calculate the forward metric, is this forward metric in the log domain plus the log of this plus the transitional metric that is the log domain, that is e raised to basically the distance associated with this, that's the distance associated. Then you store that, and then you take the min of these two metrics, and then the winner will be same operation carried out. Everything will be carried out. In fact, you don't, algorithms don't even come into picture. Everything that matters is okay. Right? Give off. Well, if you take a negative of this, then negative will end up with. Okay, now how do you calculate the properties of the source, digits, and channel? Just explain it. 0, 0, 0, 1, 1, 0, 1, 1. And we already said that the states are IT, IT minus 1, and so on and so forth. So this is IT. So in how many positions 0 appears? 2. Okay. And if you know the state APPs, conditional APPs, all you have to do is, to get the APP of this digit 0, all you have to do is sum over get the APP of the bit 0 given the entire receipt. You want the APP of the bit 1 given the entire received sequence for this position. For the next position, again, understand? So from the state properties of the source. connections, right? Whatever it is. All these transitions are there. They are labeled 0, 0, 1, 1, 1, something like that. So there are many of them. If you want the APPs of the channel digits for this position, take 0, you look at all the transitions that have 0 in that position and calculate those, correct all those transition properties. Sum them. 1 and you repeat for 0. Not right to that. You get to see that. For state properties, just look at the position, look at correct symbol ID where it appears. Correct the subset of those states. Sum up state APPs over the subset. One thing that we need to do is normalization. But we had these functions, we have to divide this by by 1 to this tau, the original one, right? So for that, what you do is at every stage, forget about the normalization. You get the APPs of state, and you add all of them. Okay, multiplied by some constant is equal to 1, and you know what? Otherwise, if you don't normalize, then what happens is that as you proceed towards the end, the numbers become smaller and smaller. Therefore, at every stage, you have to normalize it. Don't do that, then numbers become smaller. But if you are implementing it in the max log domain, that issue doesn't arise because the whole algorithm runs in logarithm. You get LLRs at the end. I'm not introduced what is log like. Once you know the log like, that's even much. Okay, so I want you to implement the full APP algorithm. Max. I'll just talk about what is the log. Lambda T. Lambda T is alpha T. Sigma T is. What is it? Lambda. Lambda T is probability of rest equal to m given the entire received probability of rest equal to m and the entire received sequence. Okay, that is related to the conditional state properties. Okay, lambda T. For T, sigma T is something to do with the transitions. Lambda T is something to do with the state APPs, and lambda T and sigma T is going to give you the transitional properties. Conditional transitional properties. Okay, they're different. These are quite different. This one is backward metric, forward metric at t minus 1, transitional metric, forward metric. So it's connecting this and this. Okay. The other one is simply concerned with this state APP. That is basically alpha into beta. Alpha into beta, that is basically alpha T of m into beta T of m. What's T of m? Yeah, but then there is beta T also product. Alpha T of m multiplied by beta T of m. Yes, you can write alpha T of m. Yes, alpha T of m definitely involves this. So you need this. this example, you don't need what? Don't need well, you need sigma t of m prime m anyway, and all your constant is lambda t of m. You need that is the state APPs. From that, you will get the source APP. Sigma t comma m plus m prime comma m just deals with just dealing with this. It's not giving you anything.
We can find
You need to find the APPs of these 1, 2, 3, 4. For that you need them anyway. You need them all of them. Don't need what? Lambda t of them.
m dash commands.
Okay, so what I was saying is that you can calculate these first and then sum them up. Okay, so you are saying that is there a better alternative? Well, if all these transitions are given to you, then you have the forward metric, you have the backward metric. Well, you still have to calculate the backward metric here. Okay, that's right. Okay, you may skip that. Okay, if you know all these transitions, let me just draw this. Like this. Is 0, 0, 0, 1, 1, 0, and then fourth one is 1, 1. Now the forward metric here. You have 0, 0 here. We close the summed it over these two metrics, right? And those two metrics call forward metric. This forward metric. Still some backward metrics are involved, right? Yeah, it's really connecting. See, this is connecting from here to here through the transition.
So that's
From
like
this,
indirect calculation. Yeah, some. For all ones, it will give you.
from what? There are two merging here. Two are merging. So if you do max log, you have to eliminate one. You have to do that. Then you choose the minimum over this and this if you do max log. Now all these various connections fully described, right? But if you want to get the metric or LLR or one of the source digits, there's a minimum over this state, the minimum over this metric, and the minimum metric. But to get this metric, you again have to choose the minimum over this merging. So all the information is right there. You just have to described, everything is right there. You can get the source properties and the channel properties. What you need is these metric, forward metric at this point, backward metric at this point, and the transitions. So this backward metric is just the given information you get. All you need is forward metric here, backward metric here, and the transition. Then you can calculate the source property of source digits as well as channel. That part. Okay, we'll stop here. In the next lecture, we'll talk about log likelihood ratios briefly. Not spend a lot of time. Then I will talk about step back. I will talk about R decision, maximum likelihood R decision decoding the formulation, union bounding the rates, price them, maximum likelihood sequence estimation. That is the background material needed. Limitations of the convolution. Coding gain is related to the convolution. At minimum distance gain, coding gain that you have the convolution. Then we can talk about concatenated functions. So that how they achieve capacity. About use convolution codes as component codes, where we can see that the component codes by themselves have limited coding. Concatenate them so it acts like a random. Understand the behavior of only an algorithm to implement decoding. I discussed